Hello and welcome to this IEA GHG webinar on biorefineries with CCS. We will start in a few moments. I just need to check how I can share my screen. Tom? Yeah, that. All right. Excellent. So again, another warm welcome to our IEA GHG webinar on biorefineries with CCS. Today's presenter is Kristian Melin from LUT University, and I'm your moderator. My name is Jasmin Kemper, and I'm a senior technology analyst at the IEA GHG. I'll give you first a very short introduction about who we are. We are internationally recognized as the IEA Greenhouse Gas R&D program, and we are a so-called technology collaboration program under the International Energy Agency's Energy Technology Network. Please also keep in mind that the IEA GHG is organized under the IEA, but is functionally and legally autonomous. So all the views, findings, and publications from our side do not necessarily represent the official views or the policies of the IEA Secretariat or its individual member countries. So we are part of the IEA Energy Technology Network since 1991. And we have 37 members from 21 countries, plus the CIAB, OPEC, and the European Commission. And our members are the ones who set our strategic direction and technical program. And we are clearly a technology-based organization which we want to inform policy, but we don't want to be policy prescriptive. So what are our core activities? We assess mitigation options, and the focus of our activities is on CCUS technologies. And therefore, we like to track capture technology development and cost, and also monitor geological storage performance. And we use all that information to provide our members and the policy audience with independent technical input. And another few of our flagship activities are first and foremost our technical studies. We have published more than 300 studies covering a multitude of aspects relating to CCUS. We also organize international CCS networks on several areas such as cost, risk assessment and management, monitoring, modeling, environmental research, and the high temperature solid looping network. We also organize a couple of conferences, the GHGT and the PCC. The conference series, where the next one will be in October this year, and the last GHGT was just in March. We also organize an international CCS summer school and have thus far over 500 alumni from around 60 countries, and the next one will take place in July in Indonesia, probably in a virtual format. We also undertake peer reviews for several organizations, such as our mother organization, the IEA, but also the US Department of Energy, EPA, and also CO2 CRC. And we also try to feed in our findings into the international regulatory developments, such as the UNFCCC, the IPCC, the London Convention, and the ISO TC 265. And we collaborate with a lot of other organizations, some of them quite similar to us, some of them more in the policy area, such as CSLF, CCSA, and the Zero Emissions Platform. This is a slide where you can quickly have an overview about all our member countries and our industrial sponsors that I've mentioned just a few moments ago. And with this short introduction about IEA GHG, we will now continue with the topic of today's webinar. One of our studies that's recently been published, Biorefineries with CCS. And the presentation will be given by one of the authors of this study, Kristian Melin. Kristian works currently as an assistant professor in the field of process and plant design of biorefineries at LUT University in Finland. And before that, he had worked at the Technical Research Center of Finland, VTT, as a senior scientist, and that's also where this study was undertaken. And his main focus has been process simulation of novel processes and also their techno-economic evaluation. He has graduated as a Doctor of Science and Master of Chemical Engineering from Aalto University in Finland. And before his doctoral studies, he worked in industry and project related to biofuel production, project design, and as a process development engineer. And with this, I would like to open the floor for Kristian.
Thank you, Jasmin, for the kind introduction. I try to share my screen now. Can you see my screen and presentation? Is it visible?
Yes, it is.
Good. Okay, so welcome everybody to the webinar also on my behalf, and next continue. And so first about the content of my presentation, what I'll be talking today about. So I will first tell some background to the work, and then why is biorefineries and CCS, or biofuel production and CCS, interesting, and then I will show the biofuel production processes and the biorefineries that we investigated, some flow sheets, and then I will tell some details about the calculation methods used. You can find those also in more detail in the report. And then something about the results. Let's look at material and energy balances, and also some Sankey diagrams about the carbon balances for those processes. It makes it easier to understand the results that we will say later for the greenhouse gas reduction and also the economics. And finally, we will consider then the effect of scale, and then finally some conclusions and recommendations. Yes. I don't know how much of the audience know about the topic from before, but if we first look at this picture below, so if we are looking at biorefineries, industrial plants that use biomass as feedstock. So biomass, when it grows, it takes up CO2 from the atmosphere, but in this biorefinery or this facility, often in the production process, some part of some CO2 emissions are also liberated. Some part of the biomass carbon usually goes to CO2. And what we look here in this study is that, okay, if we would also capture that CO2 that is produced in the production facility, so and we would take that and we would store it underground by we would first capture it, carbon capture, and then sequestration. So we store it, for example, under ocean floor. What does it mean for the emissions and the economics of the plants? And the benefit, why to store it under the ocean, or why to store it in the underground, is that then you can use a large amount of CO2. Also, one topic that is studied frequently nowadays is the utilization of CO2. But for example, if we want to produce chemicals out of CO2, we can only utilize relatively small amount of CO2 compared to the annual CO2 emissions in the world. And also we often need some other input, for example, hydrogen there. So we looked at this concept in the study. We looked at the biorefineries without CCS and with CCS, and both this first generation feedstock, for example, like corn, which are often edible, and then this second generation feedstock, for example, straw and wood residues. And we did this report at Technical Research Center of VTT together with Ilkka Hannula, and I present the work here, but we did, and probably Ilkka is also online, so he might be able to also to answer some questions, at least in the chat. Okay, let's then go on. So then why is this topic interesting? Well, quite often, let's say we talk in the media that are biofuels useful to reduce CO2 emissions of fossil fuels or not, and we talk about the emissions and the economics of those, but not so often we mention that actually if we do combine the CCS to the biofuel production, we can actually reduce the emission and we can get even negative emissions in some cases. And why it's interesting to combine this CCS to biofuel production and not only, for example, the power plant is that actually in some of the biofuel processes, for example, if we think about ethanol production, there we get almost 100% pure stream of CO2, which is automatically separated from the product. It's much easier to sequester that product than if we have to first separate CO2, for example, from flue gases that contain 12% of CO2 or something like that. So that is why this topic is interesting. Okay, then if we look, I try to move this window a little bit. So then on the next slide here, we have the cases that we considered. So first of all, we looked at corn ethanol, or ethanol production from corn. That is a typical process. For example, in the US, of course, you have other feedstock also, and it's commercial technology. So we looked at that case, what is the cost and the emissions without CCS and with CCS. Okay, then next we wanted to look at these technologies where we can produce advanced biofuels. So first of all, we looked at this ethanol production from wheat straw, because that is second generation feedstock, and this ethanol production from wheat straw, it's somewhat easier than, for example, to produce bioethanol from wood. There are plants, I think currently even this plant by Clariant is being built in Romania, if it's already not started. So there have been several of these plants lately. And then other common technology, thermochemical, this is thermochemical closure technology, then this pyrolysis oil production. And this is basically so that this technology so that we make this kind of tar-like oil, and now there has been one plant in Finland, this Fortum, but also in Netherlands there is one BTL company. They have recently sold several plants to Finland and also to Sweden. So here we can produce a product that we cannot directly use as transportation fuel, but that can be upgraded to transportation fuel in the oil refinery, and there is a lot of development on this later. Then we looked at the Fischer Tropsch liquid production. So when you gasify this liquid and then produce this hydrocarbons liquid by gasification, and here for these cases we have this we have included several cases where for the CCS we have one case where we take the CCS, which is most easy to capture from the high concentration stream, but then also for this we have a case where we take almost all the CCS max, when we take almost all the CO2. And then finally we looked at the hydrogen production, and of course this these were those technologies that we see that could have a like impact, let's say 2030 in the near future, and which are at a fairly high TRL level. So of course there are other processes also like hydrothermal liquefaction, but there maybe this technical readiness level is not yet so high. And for example, this hydrogen HVO fuels, that is also common nowadays, but there is not as high potential from that process to recover any CO2. So these are also processes where we have CO2 produced as byproduct. Let's then look a little bit more about this process flow sheets. Then this corn ethanol process, so it works a little bit similar and when you produce vodka. Basically this corn is milled and it's liquefied, and so some part of it dissolves in the liquid, and then the starch is saccharized, so it's turned into fermentable sugars. And here in the ethanol fermentation, automatically from the fermentation we get a stream which contains a really high fraction, almost 100% of CO2. So if we want to use that, that can also only needs to be dried and then compressed to high pressure. And here we also then get this solid residue, which is typically dried, so the DDGS. And then the ethanol can be easily separated by distillation from this aqueous mixture, and then typically we also have to use then another technology, for example molecular sieves, to dry the ethanol to final purity. If we look then at this how to produce this cellulosic ethanol from wheat straw, then we have to work a little bit more on the feedstock so that we get fermentable sugars. And I just move this control a little bit to the right. So here first the size of the feedstocks is reduced, and then we can do this hydrothermal pre-treatment to dissolve some part of the hemicelluloses at for example with water at about 200 degrees, and then we can use enzyme to break down the cellulose parts to sugars, and often this lignin is separated before then the fermentation, and then similarly as in the previous case, this sugars, they are then fermented, and you get the CO2 stream from here. But what is different in this case is that not all the sugars are typically fermented, but some remains unfermented, and you can often it's common to still like process this wastewater, for example with anaerobic digestion, and then you get some biogas also here. And this olive part contains a lot of lignin, and of course nowadays there is a lot of application for lignin. What is maybe the standard way nowadays is that you will burn that residue so that you will get steam from this process. If we then look at the pyrolysis oil process, so here we have to reduce the size of the feedstock and dry it and heat it up really fast in just few seconds and cool it down very fast. And after cooling, we get this star-like oil, which is called pyrolysis oil. When we do it fast, we get this maximum yield of that oil. And then the uncondensable gases and then the char residue, they are usually burned in the separate stage. And then the heat from the combustion is used as heat source in the process. But if we want to capture CO2 emissions from this process, we then have to separate the CO2 from the flue gases here, for example with amine scrubbing. And if we then look at the Fischer-Tropsch liquid process, so it works a little bit like combustion here within the fluidized bed, but we don't feed enough oxygen, so everything is burned, but instead we get this mixture of carbon monoxide and hydrogen, and of course other components, methane and tars. And then in the hot gas filter we can separate out some char, and then my former employee VTT studied a lot this process where you get rid of the tars, you can do this catalytic reforming, and then you will get more clean gas that you can scrub with a water scrubber, and then you have to increase the pressure of that gas also in order to make a chemical synthesis here later. And if we think about CO2 capture from this process, you anyway need to remove most of the CO2 and also H2S in that process. So therefore it's attractive for CO2 capture because you anyway get this stream of CO2 here. And just in this concept, some part of the char and some gases that need to be purged from the process, they are burned here. In one concept, we also look at this when we also capture the CO2 from that part. And then this hydrogen process, it works the similar way as the Fischer-Tropsch liquid process, the first part, but then also water gas shift reaction is needed, what we don't show here. So that part of the carbon monoxide is converted with water into hydrogen and carbon dioxide. And here the process works similarly as for the previous process, but then we can using this technology, PSA or pressure swing absorption, we can separate the carbon monoxide from the hydrogen. And here also we burn some residual gases and char, and from that part we get flue gases. We also looked at the concept where we separate this CO2 from the flue gases also, not only the one that comes here. Then, okay, how we then, I just check how much time I have. So, of course, one challenge when we calculate or estimate the investment cost for this kind of plants which are developing technology, so it's not so easy, and okay, there are of course literature correlations into literature and so on, but and it's typical that the first plant will be more expensive than the later ones because of technological learning. But how we did in this study was that we used this so-called reference plants that are for this kind of similar technology. So for example, the corn ethanol, we have of course the information from the commercial plant, what it costed, and we transformed this cost to 2018. And the only difference is this cellulosic ethanol case. Here we also have this mass and energy balance from the Inbicon plant in Denmark, what it cost, but because this was very small scale cost, we also looked at the cost estimate made by the company E4 Tech. They have estimated what the cost is for several of these new like lignocellulosic bioethanol plant, and we used that value. For pyrolysis oil, we use this value from the Finnish Fortum plant, but I have seen that the other technology in Netherlands, BTL, BTG, they have also similar order of magnitude this cost for this scale. And then for the synthetic biofuel production, we use the estimate from Gothenburg. And okay, as I mentioned already previously, we used for the ethanol cases, we used this input of mass and energy balances for the corn ethanol, and then for this like commercial plant, Decatur plant, ADM plant, but then also for this for the demo plant from Inbicon, because there are of course a lot of studies available what is the mass and energy balance in lab scale, but you don't find so much of this reported data on higher for example from a demo plant. And then using this information as input, we then made Aspen simulation models, and for the gasification pyrolysis we used those, and with those we then estimated the mass and energy balances for these processes. However, we had to use a little bit different scale for the corn biofuel ethanol plant compared to the cellulosic plants, because we thought that it would be unrealistic that we would have so huge plant for the cellulosic advanced biorefinery plants than the corn ethanol plant. So therefore we used 5 times smaller capacity for those. There's a lot of more logistics challenge when you have to collect this for the lignocellulosic plant. You have to collect from a large area this biomass. Then some details about the calculation. So of course, after this drying and then this compression, still you need to transport this CO2 and inject it. So we assume the $15 per ton cost for that. And actually for those ethanol and also the gasification case, not the CCS max case, the additional investment for the CCS part is quite small because you only need to dehydrate and compress this like gas, because also in the gasification case we need to remove already in the biorefinery the CO2 for the Fischer Tropsch liquid and also for the hydrogen. So we use this literature value for that part, scale to the right capacity, and also then we consider from the flue gases, we consider that we will use this quite standard MEA, like monoethanol amine technology, and for that we found the reference cost from the literature that we then scaled to the right time and capacity. Here are some other economic parameters that we used in the calculation, like how much you have to pay back of the investment each year, so 12%, and the rate and payback time and annual runtime 8,000 hours and annual operating and maintenance cost, and then the cost for the feedstock and electricity and natural gas. We have to use that in corn ethanol as source of heat, and then the value of this co-product DDGS. And I already mentioned the CO2 transport and injection cost. And then we did also for the GHG emission, we did some calculations. So if we want to compare that, how much the emission will reduce if we substitute fossil fuel with biofuel, we then have to compare it to some certain type of fossil fuel. So we use this kind of value for petrol and diesel, and then using the value for natural gas and assuming the standard efficiency in steam reforming, we then ended up with this estimate for fossil hydrogen. The references can be found in the report. Then for the upstream emissions, I mean those emissions before the processing facility from agriculture and transport and so on, these can be seen here below. For corn ethanol, there is a bigger contribution here, and we are counted also for the efficiency in the plant, that of course, that how much waste wood you need then in the process. Then, okay, if we go to the results, so let's first look at the Sankey diagram, how the carbon behaves in the biorefineries, because that makes it easier to understand the results and so on. So if we check that, for example, the corn ethanol case, 100 units of carbon comes in with the biomass. Here, 42 units goes to this fuel ethanol and 37 units to the co-product DGGS, and 21 units ends up in the CO2 fermentation gas, which is produced here. If we look then the case with cellulosic ethanol, it's slightly different. Here the biomass, it contains not so much carbohydrates as this is corn, but it also contains quite a lot of lignin. So big part of this carbon goes to the lignin residue, and also 41 units ends up here in the fermentation, and only 19 units ends up in the fuel ethanol, and 10 units ends up here in the fermentation gas. And 12 units go to these residual sugars that are turned into biogas. So if if we only capture the CO2 from the fermentation gas, of course we will capture only small amount of CO2. But in this case where we capture the maximum amount of CO2, we also do the capture for this for the flue gas that comes from lignin and biogas combustion. There we can capture much more CO2 or much more carbon. And then the pyrolysis oil case, here about 60% of this raw material carbon, which is wood, ends up in the bio oil, and 40 units ends up in this char and this purge gas or these uncondensable gases, and we can about 36 units we can recover here, and there are some losses here because when we do this chemical absorption or this with the monoethylamine technology, we assume that we capture rate is only 90%. It's not so high. And in this gasification case, then here I don't see it so exactly because I have this bar here. I try to minimize it maybe, or maybe I just go here. I remember here this syncrude about 30% ends up here, and significant amount of CO2 we can obtain from this process. So here is the standard case. But then, okay, if we want to recover maximum amount of CO2 from that process, then we can do so that we also take this, what normally is combusted in a separate combustor, this char and purge gas. So we also do the CO2 capture for that part, and then we can recover much more. For the hydrogen case, obviously, since hydrogen don't contain any carbon, so everything in the process, almost everything turns into CO2, and we can really recover a lot of CO2 here in the process. So here is the basic case, and if we also then capture from this combusted char and off gases, this also recover from those flue gases the carbon, we can capture maximum amount, so even more there. Now, if we then look at the mass and energy balances, just checking how much time I have. So then we can see the amount per dry ton of biomass that we can capture for each process, and then also we can check the biofuel yield per ton of biomass. And of course, one challenge is that different biofuel product, if we just look at the liters or kilograms, they will be very different because the energy density is different. But one way is to look at this energy content of this fuel product, and then look at how many liters of petroleum would be equal to that amount of energy. So then the comparison is on equal basis. And here we can see that, and that what has the highest yield has the highest efficiency, this process. So actually we can see here that this hydrogen has the highest biofuel yield of these processes, and also this pyrolysis oil production. This is directly the pyrolysis oil, not including any upgrading. So this has the almost as high contribution. Also the corn ethanol has quite high yield, but on the other hand, if you look at the cellulosic ethanol production, as we saw also in the Sankey diagram, the small part of carbon ended up in this ethanol. So here also similarly, this yield is quite low for that. And if we look at the amount of CO2 that we can capture for each process, so for this hydrogen case with maximum CO2 capture, here we get the highest amount. And also like for the fisted drops liquid, this is quite high, this amount. And here it's for the ethanol case, cellulosic ethanol, it depends really now that if we only capture the fermentation gas, the amount is very low, but if we also capture the CO2 from the flue gases, it will be quite high in that case. If we then go on, we look at the results for the emissions, so greenhouse gas emissions. So if we look at the different processes, all other processes except this corn ethanol can give carbon negative emissions. And here we have the upstream and processing and total contribution. And if we now, the previous slides was per ton of dry biomass, but here we look at the megajoule or biofuel produced, and the most negative is here this cellulosic ethanol with maximum CO2 capture. This gives the most negative emissions per megajoule of fuel produced, but because the fuel yield is here so low, so this is I think a little bit still, even though this is so negative, this emission, this is not so promising due to the low fuel yield. So I think it makes more sense to do the comparison on ton of feedstock. But still, also this physiotropes and hydrogen, they have quite high negative emissions per megajoule of fuel. Then if we look at the estimated investment cost, here we have the different processes. We have without CCS and with CCS. One finding I think is that if we compare the cost of the biorefinery or biofuel production plant and then the CCS part, actually the CCS part, except perhaps for this cellulosic ethanol maximum case, it's quite small relative to this total cost. Then if we look at the levelized cost of fuel and cost of CO2 capture, and here we look at the levelized cost of fuel, we again look at this liter of petroleum equivalent. So it's here, and then we have here the cost of CO2 capture. So I think one finding is that this levelized cost of fuel, it didn't increase so much for most processes when we included also the CCS. Here for the cellulosic ethanol maximum case, it's somewhat higher here, but for the other process it doesn't make that big difference. And the cost of CO2 capture, it was for these streams when we already have from the biorefinery process a high concentration stream, it was quite similar amount, roughly $22 to $24 per ton. And then for this pyrolysis oil case, where we only can capture the CO2 from the flue gases from low concentration stream, then it was a lot higher. For those with intermediate costs, this process is so that you need to capture some part of the CO2 also from the low concentration streams. If we then finally look at the effect of scale, so here is the plant scale barrels per day on petroleum equivalent and the different technologies with CCS included. So actually, I think that this scale has a big positive effect on the economics of this levelized cost of fuel production than the capture cost here, and which makes sense because it's the biorefinery, its investment cost is so much bigger compared to the CCS part, so it makes a bigger difference. And if we compare the different technologies here, so those with more expensive capture part, for example, this pyrolysis oil, they benefited more from this increasing scale than this with simpler these processes where you only need simple CO2 capture, which makes sense. And of course, it's usually so that in process technology, that the bigger scale you have, the cheaper it becomes per unit of product. Then my final couple of final slides about the highlights and conclusions. So okay, we studied here 5 different approaches to biofuel production, and we evaluated them from techno-economic and greenhouse gas reduction point of view. And all cases except this corn ethanol resulted in carbon negative emission due to capture of this biogenic carbon. And as I said previously, this CO2 capture for these high concentration streams because the technology was the same and there was not so big impact of the scale because that part was quite cheap. So that was roughly 22 euros per ton, but then for this low concentrate streams it was 66, not sorry euros, but dollars per ton. And highest amount of CO2 per ton of biomass we could capture for this hydrogen case. But if we look at the megajoule per fuel, then this cellulosic ethanol case had the most negative emissions, but that was not so promising due to this low fuel yield. And then so then some about the conclusions. So to sum up, I think that it is biorefineries, what is different with them compared to the biomass power plant is that then some of them have really these high concentration CO2 streams, which makes also the CCS more feasible. But however, we should keep in mind that the biomass availability and then the locations where you can do this sequestration of CO2, they are not often at the same places. And one challenge is that, of course, this deployment of both these advanced biofuels and CCS, they have been very slow, and if we combine them, this will not solve that problem. I think what the benefit would be that when we have these advanced biofuel plants, probably we can reduce then the reduction on cost of CO2 by combining CCS in those plants. But still, of course, in the cost estimate, there is a quite big uncertainty. So we need more plants at this relevant scale. And also when we have more and more plants, then the cost will go down because it has been seen in many cases that the first plants are really much more expensive and they need economic support to be economically viable, but then after you have constructed a certain amount of real size plants, then the costs go down. So I think here is my final slide. So thank you for listening, and in case you want to contact me, here is my contact info. Maybe I could say two quick things in the end. So actually we have also processing this result together with Ilkka. We are planning to make it a scientific publication out of it. And then as one final thing, I could mention that in my present job at LUT University, I will also look one idea when there is like this when you use CO2 to this CCU. So I will check that if you would do a special case that you would take the lignin out of biorefineries and then you could make plastics out of CO2 and hydrogen, and you could make a composite of those two. So I will check that what would this be promising and what could be the techno-economical feasibility of that concept. Yet I don't know how that will turn out. So thank you. I think that was all what I wanted to present now. So
yes, thank you very much, Kristian, for your very good presentation, and would like to remind the audience to please put forward questions if you have them in the chat function, because I've scrolled through and have not seen any technical questions so far. So maybe we can first address the couple of more formal questions. There were questions whether the report will be available, and usually, because we are a kind of member-funded organization, our reports have kind of a 6-month embargo period in which they are only available for our members. And for this report, it was published in March, so embargo would end sometime in September. But we decided we will make the report available directly after the webinar. So if you go to our website, maybe tomorrow or later today, you should have access to the report there. So I'm still not seeing any questions. So while we're waiting for questions, maybe we can maybe talk more general. I mean, regarding those, you mentioned there are not enough or not enough certain or good quality data in order to have a very solid analysis. And are you aware of any planned projects, especially also in your local context in Finland, that could help providing better databases? And or which projects are there in the pipeline generally? And how does that match?
I think it's quite technologically specific. For example, I mentioned the pyrolysis oil production. For example, in Finland, in East part, we have now a facility coming up. So I think at least on that technology, there will be more data available. Right now, I'm not aware so much about new big scale gasification plants that would use biomass as raw material.
Okay, and I think we have one question there. Do these simulated scenarios include the difficulties of getting permits for the CCS implementations on the refineries? From my understanding, many industries who consider CCS for their combustion and process emissions are discouraged due to the complicated permitting process that takes up so much time to even gain access to implement. That's one question from the audience.
Yes, thank you. That was a good point and good question. We didn't look here at the permit in this work, so I'm not aware of what this permitting process will be like, but that is something definitely to consider in future work.
So I've still not seen any, but I think I probably cannot see all questions are. On another note, if we are, will these studied cases provide detailed information on different emission rates? Someone from the audience is interested to learn how the different feedstocks and the different end products have different emissions in the end.
Yes, I think that, okay, we see quite a big difference if we look at first generation feedstock like corn, and then if we see look at the second, like lignocellulosic biomass, because if you have first generation material, then okay, also in the agricultural phase there might be this, you need this fertilizer and everything, which there are emissions with that. Then I think if we have then if we have thermochemical processes, I think that the emissions between, if it's wheat straw or then wood, they are not that different. It mainly depends that how easy those materials are to how easy they are to process with the different processes. And it depends really, of course, the emission, it depends really, one thing that is really important is the yield of the final product. The better the yield you have, the lower the emissions per product will be. And
okay, now we have a couple more questions about the technology of extracting CO2 from bioethanol. This is quite effective, but would it not pose kind of a risk or have knock-on effects of more land having to be converted for fuel production and thus limiting food production capabilities? It's the food versus fuel debate that's, of course, ongoing.
Yes, I think this is a good point, and of course we have not here in this work, we have not looked at the indirect effects so much, but I think that it would not maybe make sense to create new first generation bioethanol plants to even if we include CCS in them, but maybe it would be wiser that if we have the existing first generation bioethanol plant and see if we can include CCS to those to reduce the emissions.
Yes, I definitely agree. It would make much more sense to not really completely avoid, but alleviate this question by focusing on residues, waste residues, and so forth. Yeah.
Yes.
Then there were two questions about what economic incentives exist or are being proposed for rewarding negative emissions.
Yes, I'm actually not currently aware of any incentives to like enhance negative emissions. I don't know if my co-author Ilkka is also here, if he has any idea of those, but I'm not. I think it has been a challenge that there has not been incentives, at least earlier.
Yeah. As far as I'm aware, currently the European Commission is currently thinking about launching an EU negative emissions trading scheme. I'm not sure whether that will be integrated in the EU ETS or whether those will be parallel platforms, but as far as I'm aware, it is at least considered and discussed, and there is work on that going on. And just as also one attendee, maybe not so much a question, but also more a statement that it might be important to consider more the CDR, the carbon dioxide removal service from those plants, rather than only focusing on the traditional techno-economics of those processes. Because in the end, then if the negative emissions price is like high enough, you might have more revenue from selling negative emissions than from the actual product. So that's something that
I think that is good to point out.
Yeah. Then we have maybe a more direct technical question. At what state, temperature and pressure, is the CO2 leaving the plant site, and how are the economies of scale for CO2 compression compared for a small plant like ethanol digester versus a large plant, for example, gasification?
Yeah, I think in this design what we had, for example, if we have fermentation there, of course, to start with, and I think also for the other technologies, if we have gasification and hydrogen production, the CO2 is produced at quite low pressure in ethanol, 1 bar, and okay, if it's gasification process or something else where we separate, it could be a few bars in the regeneration of this solvent, for example, amines. What we then have assumed that we will then compress it to 150 bar. So it's like first we dry it and then we compress it to 150 supercritical states, and after that it's transported. We scaled this, we had an estimate from literature how much this part to compress it and dry it would cost, and actually it in those scale that we studied, it didn't make so big difference. But of course that if we would have a really small bioethanol plant or something, then it could be maybe significantly more expensive in that small scale.
Okay, thank you for that answer. And maybe one last questions or maybe also some pointers for future work. Or what do you think about the electrification of certain parts of the process? For For example, if there are natural gas inputs somewhere and if they would be replaced by electricity, how would that change the cost calculation?
Yeah, I think it depends a lot on the emission footprint, how does electricity is produced, but I think definitely it makes sense to electrify some parts of the process, perhaps also in gasification. When you have the reforming step, it makes sense. But if we think about corn ethanol, for example, maybe it would even make more sense to and that we looked also in the report that, okay, if you would not use natural gas to provide the heat, but you could, for example, burn wood chips or something like this.
Yeah. And maybe we have one final question. That's also a more specific one. Do you consider the economic analysis based on first-of-a-kind plant methodology accurate for the Fischer-Tropsch liquid and hydrogen production plants? And then some further elaboration. The Gobi gas plant is a SNG production plant based on biomass indirect gasification. However, the studied cases are Fischer-Tropsch or hydrogen production plants based on biomass direct gasification. Therefore, the cost estimate is expected to be different. And moreover, Fischer-Tropsch and hydrogen plant cost difference is reflected only in CCS components.
Yes, I think it's a good point. Yeah, and question. So, yeah, of course, there are many different way to do this cost estimates. Another way would be that we would have calculated for a mature plant. There are plenty of estimates for Fischer-Tropsch liquid, and I know this Gobi gas plant, it was for SNG, but at least the gas purification is quite similar. I think it maybe would make sense in future work to like make a little bit like this sensitivity analysis. So look, for example, for the hydrogen and Fischer-Tropsch case that, okay, if we would have, for example, the cost 30% lower than and what it's now assumed for the first of a kind plant. So would the results still be similar or how? Because there will be anyway quite big uncertainty in this estimate that even if we use this like estimate for mature technology, that of course when we then have when we have the first plant that produces Fischer-Tropsch liquid from biomass, after that we will have a more exact estimate of that, what would be the real cost to produce Fischer-Tropsch liquid.
Yeah. Okay, thank you very much, Kristian, both for your presentation and also for answering all these questions. And I assume if someone has a question that hasn't been answered, you would be happy to answer via your email, which is
yes.
on the last slide.
Yes. So thank you a lot. And
yeah, and of course also thank you everyone for attending this webinar. We were very happy to have you. As we've mentioned before, any additional questions, please send them to Kristian, and the recording will be available shortly after the webinar. It takes some time to compress the recording, and also we will make the report available later today. So thank you all for attending, and I wish you all a nice morning, afternoon, evening, wherever you are, in which time zone. Goodbye.
Goodbye. Have a nice day.